So what actually he could do with the secrets, right? He stopped there. So a few months later, we received another submission. Again, the same pattern repeated. Secrets were found in the JavaScript bundle, and then he did not investigate it further. So at that time, when we received all these submissions, just a few months on, nobody actually kind of asking the question why these secrets keep finding in one time, right? So what actually finding happen if you have secrets in your production applications? What actually these secrets will unlock, right? So nobody asked that question. So what I did was I went back, started reading the JavaScript file, not just to find secrets because secrets were already there, reported for, but to read it as a map to understand how the application was built and functioning and using these secrets for. Because in the modern day web applications, the API points and scripts and pretty much, everything is hard-coded, documented in the JavaScript file because the front end needs the JavaScript file to interact with it, right? So that's where it happened. So 2 submissions came in, and then what I did using those credentials, I called Azure AD token client and I was able to read every account in the system. So we're going to see that in 2 exploitation chains in a few minutes. So number 1, exploitation chain 1. So the Azure AD chain, right? So this is how it's going to look like, JavaScript bundle. Throughout the top, we're going to see the demo portal. It's called Insecure Shield portal. So any credentials or any, accounts or secrets you see, it's completely, fake. So, it all starts with the view source and slide we're looking at. So it has main.js file. This file is not written by developers. So this is an auto-generated file, right? So the build pipeline builds the artifact. It generates the artifact. And then it makes credential syntax, and this is an auto-generated file toward the guild pipeline. So what actually we're looking at, it's an Azure AD configuration. App ID is a public identifier, which we always see it, client side to IDs, right? So, app ID is like a client registration ID, and app key is a secret that should never be in front-end sources anywhere. JavaScript files and configuration files and APIs anywhere. So that should be on the server side. The resource ID. So what the resource ID is going to tell, the resource ID is kind of, it identifies what the token is for. Like, what it wants to access, right? An API or a specific resource. It tells Azure AD, hey, I want to access this specific resource in API. And subscription key. It's like a pass key that your application has, that your API has to pass through ABM gateway. So ABM gateway validates your, specific, API. It's going to look for access token, and that's a specific subscription key. So without the subscription key, API management gateway is not going to allow you to connect to the back. So these are the 4 values. And what actually these 4 values, if you have, what you do, right? You could call an Azure AD token. And that's what we're going to say. So I started reading the JavaScript file, put together all the 4 values that I have C, and then call Azure AD with the app ID and the secret key. And what it's going to do is Azure AD validates the supply credentials, right? App ID and the secret key that you supplied. It's going to validate it, which is immediately going to generate you an access token. And I use that access token to connect the backend API through API. So I have an access token at this point, and I already have a subscription key. I used both subscription key and access token and sent it via an API to the backend API. And the backend API has written the configuration of the API that you were specifically requesting, right? Why this was happening? The reason it happened, we're going to see it in the next slide, because it has the token generated is an access token that we have the service principal permissions. So anyone with these 4 values that you find in JavaScript files, you can become the application yourself because you're going to use the same AD token. You can call AD token, authenticate to it, generate an access token, and you're connecting to your backend Microsoft API. So this is the standard documented, Azure OAuth 2 token. So the 4 values that we find, we're going to just paste it here, and we're going to send it to backend API. So we're going to generate an access token, right? From 4 values, we can take our entire, you can read every account of the system. So I built a tool, purpose-built demo portal. That's where we're going to see it now. So this is where all it begins. So you have the JavaScript files inside it, and the main.js file, which contains the core application logic for an application, right? So what a pen tester or a bug bounty researcher or an attacker will start here, right? That's where they're going to look for everything. They try to understand the application. So what I do is pretty much look for keys, and you see there are many documented keys, and this specific one we're looking at the Azure AD configuration that we have seen in the previous slide, right? So I use this, use the burp suite to connect it, and then I plugged all the three keys that we have, and immediately it generated an access token. So I use the access token again. So where do we find API endpoints? Developers make it easy for all time for testers. So, bug bounty researchers. So the key is again itself in the JavaScript file. So there is another API app.js file where you can find looking for API endpoints. So this is a construction of like how the application is designed and using these APIs. So it has everything documented, API/login profile, everything, right? So I use one of the specific one to construct. So that's called API users, right? And then I went back to burp suite. I pasted back the access token I received and subscription key from the JavaScript bundle, and it was able to provision all the accounts in the system. So from this, you can see it has password hashes installed, right? So I can use it to decrypt and construct a password with it. So that's what I use. I created a script just for that to show, and then use this to just decode the password for the account, and then use this to log into that particular account. So that's how the first attack was done. From 4 values, I was able to read all the accounts in the system. So why this was possible, right? So there's a difference between the app token and the user token. So the reason this has been possible because the token that has been generated is a service transport token. That means it has the application permission. It has the application identity. So when I use the token, when I send that request back to the Azure AD in the back, so I got all the details because the token is authenticated with the app identity itself. So the highest flow of permission it has within your entity, right? So that's the difference between the app token and the user token. So where the user token has a delegated permissions, where only the signing user can, even though the token can do what the signing user role has permissions to. So the blast radius, if it was possible, right? So in this case, what an attacker would do is not stopping there. So the blast radius is going to look like, based on the permissions the app token had, they can read for files, they can use PI, they can use APIs, they can do it for level movement, they can call API data, everything. So exploitation 2 is the crypto.js chain. So this creates a false sense of security just because the developers, some developers, they know that, documenting the keys inside a JavaScript file is bad for them. So they started using the configuration, crypto.js AES encryption to encrypt the configuration. So it's going to look like, a not readable string sitting in the JavaScript file. So I can't read it. But the important fact is the browser has to understand. The browser needs that keys to connect to the back, right? So where does the key live? If the browser has to connect, the secret must be in the browser itself. So one of the 3 keys. So the core principle, client-side encryption cannot protect a secret from its own client because the browser is decrypting, right? So the key has to be fetched by the browser in one of the three ways. The key must be sitting somewhere in the JavaScript file. The function, the app calls to decrypt, it has to be there. So, or it has to fetch its own endpoint where it can fetch these decryption and use them with combine with the function and decrypt it so that it can communicate back with the backend application. So this is what it look like, the encrypted blob storage and the ciphertext key, that's decryption key, just sitting 3 lines below the code. And you can see the function that's, to decrypt, combining both the encryption key and the decryption key, and the browser will be just decoding that just in a matter of 5 seconds. So we're going to find that again. Let's switch back to the browser. So that's the encrypted blob storage. And that's where the decryption key lives inside. And that's the function that's using the encryption and decryption keys so that the browser can decrypt it. So what I did is, since I have the decryption key and the blob storage, I was able to just use it just to decode it. So the credentials came back. So what I could do with this credential, so this time it's different. It's because this had more NP-level credentials. So I use this token, I use these credentials again, went back to Perp Suite, constructed it. Use the same secrets and generate an access token. And again, went back to my app.js file that has the API endpoints documented. And use this token and subscription key again to call internal configuration, and it has returned to the database connection strings. So this is what we have seen, right? So it has the encryption configuration and then one decryption layer just sitting there, and as it goes, it's just one extra step, and the browser just going to decrypt it. It's in this same file. And this is the dump, what the dump looks like from the encrypted blob storage that we have just seen. And so the important concept here, both applications pass every shift-left scanner. Azure AD credentials and crypto.js for all the secrets on both these exploitation chains. Both these two applications, two different applications, different developers. The source code is means scan by every shift-left scanner. But the credentials still passed the scanners and somehow got back to production. So what the security tooling was not working now. They scan GitLeaks on every commit, SAS on every pull request, and they have GitHub secret scanning that does the active pattern research matching on all the GitHub repositories. Yet the credentials still went live production. So where's the gap, right? So shift-left tooling scans what you commit, what's inside your code repository. So if we take a look at the pre-deployment scan, so what we have seen, so GitLeaks, GitHub secret scanning, SAS, they scan what's inside the code. Once it's been scanned, once the code has been scanned, once the build pipeline runs, so that's the layer, that's the merge boundary. And once the merge boundary has been done, so your application will be stood up by the pipeline, and then the dash scanning will happen. So the post-deployment scans. So what's the runtime dash scans today we have are all active crawlers, and they will look for injections, misconfigurations, authenticated issues, right? They're not specifically designed to capture credentials in runtime security. So taking a look at exactly again, a step-by-step process. So developer writes code, they commit it to your repository, and GitLeaks scans, GitHub Advanced Secret Scanning happens, and then SAS secret scan. That is the last step where your code gets the scan coverage. Once the build pipeline starts, artifacts get produced, and the artifacts bundled, and then deploys to production. There is no secret scan or no scan happening between your build and deployment. So these are the 5 structural paths and plus a bonus, how secrets scale into production applications. So build time and alignment injections, CI/CD pipeline variable substitutions, lazy loaded chunks, and SSR state serialization, and one-time API fetch configurations. And the sixth one, which is familiar, like, developers most of the time find their credentials, they will deal with the suppress defining as it's a test token or it's a false positive. So these are the 5 reasons how, the application, so how the source code credentials get baked into your artifacts bundles and delivered to production. We'll take an example. So the developer stores a secret in an environment file. That environment file usually is in gitignore state. Nobody can commits the environment files or configuration files to GitHub, right? Code repository. So what happens if they commit the code configuration files or the environment files? So once it commits, so GitHub, Truffle or any shift left scanning, they're specifically designed to catch these specific keys, right? So they detect it and they block it. So your build is blocked. It's not moving forward. So what happens if a developer stores a secret in an environment file and the environment file is in gitignore state, right? And the gitignore, the environment file has the .environment file is in gitignore state and it gets committed to code repository. The code repository will see the variables. It's just going to see the variables, right? So shift left scanning happens and then it will see the placeholders and it will say, okay, it's not a credential. It's just a placeholder. So I'm going to pass it. So it will report all green. So once that is done, the build pipeline runs, the environment files, the environment file, the build artifact scanning will begin, and then the define plugin, if it's based on your applications, right, the technologies, it's React, White, Vue, different application technologies that you use. So take an example of that specific create React application. So the environment file, so once the build pipeline begins, the define plugin will read the environment file. It gets the credentials and bundles into the artifact and then delivers to your production application. So everything to the left, that's where the last scan, where you see it gets the code gets the coverage. And everything to the right, there is no specific coverage because scan is not happening between build and deploy. So that's what the map looks like here. For path A, in the code, the environment files or the configuration files get committed to Git repositories. It will be captured by, it will be visible and it will be captured by the repository scanners and the build is due live. So one of these 5 paths where, pipeline substitution or state serial injection or, runtime fast configuration. There is no detection. So the shift left scanning going to pass it and you will find this to the production. You will find credentials still in the production. So the landscape, if you take a look at the landscape, so shift left, industry has heavily invested into the shift left scan. So we have many source secret scanning or port scanning coming in picture. But what we have on the right side, on the shift right, there's nothing, almost nothing on the shift right gap where it's going to look for JavaScript bundles, where it's going to look for, configuration files anywhere. So the runtime security where the dash scanning piece, once your application has been stood up, there is no secret scanning happening on the runtime layer. So different tool categories that we'll put into. So we have GitLeaks, the top 2 are the repository scanners, and Truffle has live its own space of it does live validation scan. So, and then we have active crawlers and template scanners and burp extensions. So they're actually solving one piece of puzzle, not everything together. So what actually a runtime secret scanner should really require? So it should have an eye of a hacker, just like it should see what the attacker sees. So it should see, specifically all the APIs. It should scan for your, JS bundles, JSON files, XML content, WebSockets, or anything within the chunk files, chunk JavaScript, JS files. An important concept is, or important detection is step 3, where crypto.js encryption. So like I said, it creates a false sense of security because the string looks very big based on whatever you are encrypted. So no scanner will find it, especially if you have a specific pattern, embedded into the tool itself. And fourth one, we all know any tool is going to generate a false positive. There is no tool that's not going to generate the false positive, right? So, aggressive noise suppression. If the tool doesn't limit or suppress the noise findings, so it's going to be very hard for the analyst or for anybody to review the specific, what actually the keys are, because it's going to generate. The front end is pretty much all the identifiers, public identifiers. So it's going to find almost everything that he finds in the runtime applications. So with all these four values divided together, so that specific application can find all the credentials in runtime. So two independent studies have been connected. Intruder.io, they recently conducted in December 2025. They scanned about 5 million pages and found and discovered 42,000 tokens. And in March 2026, a Stanford University professor, Hemanth, they conducted, they scanned about 10 million pages and identified 1,748 credentials, and they have reported to the appropriate ordinance species. And you can see 84% of them are living in JavaScript articles. So this just shows that, the internet scale is completely not scanned for secrets. So the attackers already know this. They're finding it. They find it, they never report that. So the runtime layer is the only layer that hacker always sees, and is the layer that doesn't have tooling, automated tooling to find secrets. So interesting question is, if somehow everybody is able to do this, read the files, create a configuration, call Azure AD tool, none of the tools will detect it. So WAF, SOC, Akamai, yeah, it's all green. You will not find, because it's stealth. It's going to look like just as an application, as a user visiting the application. So you will not see any hours anywhere. So only three things find it, just as we discussed before: head testers, bug bounty hunters, and hackers. So two of those three report, one does not all the time. So we're going to walk through a little demo of this, how to find it. So like I said, so this is a purpose-built demo portal just for this conference. I'm going to switch this real quick. So this is the tool that I built just for this purpose, to find live credentials in production applications. So what it's going to look is it's going to inspect your traffic. It's going to look for JavaScript files. It's going to look for APIs. It's going to look for XML content types. It's going to look for any WebSockets. It's going to scan based on the patterns it has been inserting it. And it's going to find and report the credentials live back here. And for the purpose, I put together like four different tools as well. So I'm putting it together like Titus, a secret scanner, and you can see the tools it has, the findings it has, and there's a sensitive discoverer. It reports based on, all these are based in regex patterns, so it will find only specific based on the regex patterns that they have been built. So TruffleHog also has a runtime security, burp jar extension, and a terminal extension as well. So that's what it will look like for TruffleHog. So I'm going to shift back here. So that's the tool. It's going to find it. So again, there are duplicates. So I built this in 4 different prompts. So a browser extension. So pretty much what we're going to do is just add this browser extension here. You could go to Chrome Store, you can find it and just install this, plug it into your burp suite, in your browser, and just enable that feature, scanning and reload your application. It's going to find credentials inside it. Oops. So it's going to find credentials. So once it's done, so the analyst will review and you can generate a neat, good detailed HTML file. It has that. And also I built a web app, a version for Mac and a version for Windows as well, just to scan for different level of, based on who is scanning it. So 4 different tools comparison. This is the 4 different tools comparison with the unique finding sets, what it's going to look like. And, so the defense, right? The remediation, that's what important concept. So every time we find credentials, when we report to the application teams, so we're going to have a chit chat with them. It's like a war room, and they're going to come back and say, hey, we found credentials, and they could come back with, we rotate credentials all the time. Well, but the credential still lives in the JavaScript file. You have to replace it, right? So, and then again, we encrypted the configuration. This is all the conversations that happens, based on the conversation we have. And again, the key sits again, the decryption file sits again in the JavaScript bundle. So can we just obfuscate the JavaScript file? Yes, you can do it, but still, it's not enough. So there are tools that are going to, beautify that and give you back. And then can I use API? Using an API, I get to fetch the runtime configuration on the runtime side. Again, a browser, opening a developer tools or using a burp suite kind of proxy, you can still see the response in the response back. So then they'll ask, okay, all questions are out, and they're going to ask, okay, what do you suggest? So then it will be it. So now we're talking and use BFF pattern. And then once we propose it, again, BFF pattern is not easy to implement just right now, just today. And then they're going to go back and yes, no, that's going to take forever. It's not going to happen today. So it's going to take me for 1 month or 2 months. Yeah. Then the heads up come in and then ask, okay, where else are we having this problem? That's an important question that comes up all the time, and things like this will find. And the management and the company, as a company, they have to look into where else this pattern looks like, right? So then they have to scan their entire attack surface, all the external assets, looking for all the secrets. So for developers, the mental model shift is based on how this is being used. The environment files, just as we discussed, in a GitHub repository with the secrets, okay, that's good. But once it's baked into JavaScript bundles, it is still public. The secrets are getting delivered into JavaScript files. So specifically for single-page applications, remediation is to use Pixie and OAuth because Microsoft uses that and proposes, because that completely eliminates the need for storing secrets for completely 100% single-page applications. So it eliminates the need for having secrets completely. It's because it's based on code verifiers. So 4 layers of defense: BFF patterns, secret managers, artifact scanning, and runtime secret scanning. Number 1 and number 2 are going to eliminate storing secrets completely in the JavaScript files. And number 3 and number 4 are going to be once something may accidentally get spilled back into the applications, artifacts. So those 2 scanning layers still has to happen so that, to have a full coverage on the left, on the right, even for the build, between the build and the deployment. So this is what it will look like for BFF pattern. So before and after comparison analysis. So before, the secrets are living inside the JavaScript file, and with the BFF fabric, it's going to be we're storing secrets in the Azure key vault, and then making, the secrets are getting fetched in the back, making communication back to your applications, and all your cookies are being sent to your application front. So this is the important slide where what it's going to look like, right? Source scanning, which happens on every organization, shift left scanning happens all the time. And artifact scanning, which is not happening, almost, I don't think, happening. So once your build pipeline starts, between the build and deployment, those scans happening. So artifact scanning will completely find the credentials. And runtime secret scanning, which is not happening today. So these are the 2 new steps introduced in the pipeline. So for pen testers, if they find credentials for pen testers and bug bounty researchers, they find credentials, just don't stop there. Look for secrets and find what they actually unlock. And important step is reporting. Responsible disclosures to appropriate organizations for remediation. So just in case the open source tool, it's available in GitHub if you want. So what you can do today is use tools to start scanning your runtime application posture. So that is what you can scan for multi-targets. You can load for 50 applications or 50 IPs, give it, and it should be able to scan pretty much everything. So the two chains that we just talked before are from authorized assessments that has been reported, remediated before this talk. Any questions? I'm happy to take it from that.
I have one for your GURP extension. Is that running live, or do you have to catch the JavaScript files previously running like in Street? Or is it running live?
It's running
application. Okay.
It's running live. So it has we can give it a target in the dashboard,
sure.
And then it's going to set it through proxy, HTTP proxy.
Yep.
So it's going to find all the JavaScript files and API console.
So it basically will do JS Finder the same way that JS Finder works, but then it will analyze for the sequence.
Yes.
Okay.
JS files, XML content types, JSON content types. It's going to look in headers because most tools doesn't scan APIs and they don't look for headers because that's where it happens all the time.
Thank you.
Yeah. Earlier, you talked about the type of token you're fine about, the service token versus the app token. Didn't really see at the conclusion. So I was expecting you to say, yes, you used the right token.
So
it wasn't clear if that wasn't a direction, like one, be aware of you're using the law correctly, or is there a different problem?
So actually the failure is having those credentials publicly that's giving the service principal permissions. Generally, it's the user token that gets to, right? So the user token has much limited access where the token can do what the user
is. The service token at the edge rather than its attention back for backup basically. Yeah.
Any other questions?
Any senator tool for this extension on Verb Suite extension? Are you relegated to just the browser, or did you expect like the JSC extensions?
Extensions you mean for
route, right? So if you have other extensions or values, these any player of your tool expect that a JSON extension.
Connect to that JSON extension, you mean?
Or expect whatever you run you can run time. Like so am I running some sort of fallback like extension you expect.
So if you turn that feature on, it's gonna scan for it. It's gonna look for it on the browser extensions.
I think what he's asking, your browser plugin, is it just target the web page?
Yes.
Target, or will it actually look at the whole browser runtime and see it?
So for that specific domain, it's going to look for an Android type browser
in that page. So you call them that whatever the page slash.
Yes.
So if 2 weeks ago, if I had opened this up in Edge, or I think everyone is aware of Edge, like decrypts all your secrets, and then you say memory, it would have dumped every secret. Well, you should just be going to RAM every time because Edge has all secrets in memory.
So this is going to look for that specific target domain.
So you're only looking at the file. Well, it's the memory filter of JavaScript for that browser session. I think that's what you're looking at. It wasn't just looking at Lambda and domain, but my browser is made up of everything that Microsoft or Chrome is running at that time in memory. It's just
you mean other files. You mean
it's memory.
Oh, it's memory. So it's not going to look for memory.
It's the whole Chrome runtime. So you're only scanning the target.
Yes.
You're actually not scanning Chrome or.
Yeah.
That's what.
Sorry. Yeah. It's not going to scan for memory. So it's specifically just for the light target on the specific what application is stored, not for any memories.
All right. Let's go around and plus them on.